Here we go. So we can start with questions if you have any questions. And the plan is, I'm going to just repeat my sentence. I just start recording. The plan is to continue working on 2.5, transformation of functions. Okay, guys, we are going to, and again, you can interject anytime and say, can you explain that again? Blah, blah, blah. So from last class, guys, I'm going to go over two of the functions that we quite didn't work on last class, and they're not that difficult. Cube root and square root function. Okay, and I'm going to sketch them. They will look a little better. I'm going to sketch them on Desmos. Okay, you can use your calculator, and if you want me to show you how to use the calculator, you just have to tell me, but I do prefer Desmos, and you will have access to it during your exam. Okay. The square root function, f of x is equal to, you can guess, square root of x. The radical sign x. And this is what it looks like. Let me see if I can hide that. This is what it looks like. Okay. It starts from the origin, goes up like this, only on the right-hand side of the y-axis. Okay. Makes a little bit of sense, guys. If you replace x with 4, 1, 2, 3, 4, you're going to get 2 because square root of 4 is 2. Now, they don't have plus minus square root of x. That means you're only looking at the positive values. Okay, keep that in mind. So let's take a couple of other ones, like 9. When x is 9, f of x should be 3 because square root of 9 is 3, and that's exactly what we get right here. When x is 0, square root of 0 is 0, and that's exactly what we get. So the graph should make sense. Okay, again, we are just taking into account the positive values. We don't care about the negative values. That's how the function is defined. Now, what is the domain, guys? If you're walking on the curve, what could be the set of all possible x coordinates? Let me see if I can write it here. The domain is going to be all positive real numbers and 0. So we write it like this. 0 is included because when you replace x with 0, things make sense. You cannot find the square root of a negative number. They're undefined. Okay, we'll just call them undefined. They're imaginary numbers, and we didn't talk about imaginary numbers. Okay, so we'll just say, so it doesn't make sense to do this. Okay, so we will ignore those in this class. All right, the range, I'm going to write r. R is going to be, again, you're walking on the curve. You're thinking about the y coordinates. They're going to be everything here. Same, exact same value, 0 to infinity. Okay. Actually, that should be enough for our transformation. I will do the next one, cube root function. It looks a little funky, but I'll do it. I don't think I'll use it way too much. Okay, the cube root function. Let's see how we can do it. We don't have a good one for cube root. That's okay. We're going to raise it to the power 1/3, and that should do the trick. Okay, this is the cube root function. Okay, let's test if the function makes sense. Remember, guys, cube root is this. Let's see. So what's the cube root of 27? 3 times 3 times 3 is 27. So cube root of, and this is how we write it. Okay. What's the cube root of 64? What times what is 64? 4. 4 times 4 is 16. 16 times 4 is 64. So cube root of 64 is 4. Let's check. We'll have a little difficulty doing it here, but that's okay, because the numbers are too big, but we'll show you. We'll show you. Cube root of 64. All right, it's going to be a bit of a challenge. I'm going to go way out there. Take a look. It does make sense. 64 is going to be somewhere here, and that's about 4. Okay, so here from 0 to 10, you have 5 boxes. Each box is 2. So that sounds about right. And take a look at 27, 27, 22, 23, 24, 25, 26, somewhere here. And that does look like it's about 3. So it is the right function, just to convince you. And the domain and range is going to be, let me go back to a nicer view. Okay, the domain of this function, again, how do we find the domain? You're walking on the curve. You're thinking about what could be your x coordinate. It'll be everything. You could be here. You could be here. If you're here, your x coordinate will be this. If you're here, your x coordinate will be this. If you're here, so it'll be everything. We don't say everything. We just say from negative infinity to positive infinity. And your range will be the same. I'll show you in a second. So if you're way up there, I know the curve goes up very slowly. It is an increasing function, but it's increasing very slowly. But if you go farther out, it'll be here. If you're here, the y coordinate will be here. When you're finding range, you're thinking about the y coordinate. When you're here, the y coordinate will be here. When you're here, the y coordinate will be here. When you're way on the left, okay, and it steadily goes down, well, it's increasing, but if it's going down this way, so it'll be all over the y-axis. Okay, your range is all real numbers. You can write it that way, or the shortcut is this way. Your domain is all real numbers. You can write it in English that way, or you can write it this way. It's much quicker. I'm going to pause here a little bit before I go over transformation. Somebody is trying to ask a question, guys. Okay, guys. So we have 2 functions here that we didn't discuss last class. We discussed it today. We should be familiar with them, and all you need to care about these functions and the ones we do in the problems. So we talked about this. I don't know if you can see it, but we have. We're going to talk about we're going to talk about vertical shrinking and vertical stretching. Okay, it's not too bad, but the next one is a little bad. I'm going to save this guy here. What's vertical shrinking and stretching? How do we stretch a graph? How do we shrink a graph? Okay, it's not really that bad. And this is not going to make a lot of sense because they are using C and all that. But I'm going to go give you some numbers. It'll make a little more sense. Then I'm going to come back to this. Let's look at our Desmos, and we're going to take a simple curve. Okay, let's take x squared. It's the quadratic function, and it's a parabola and all that. Now look at the g of x. Now, I am going to take, you can easily write this. Okay, that's what I'm looking for. Okay, but I'm going to write it like so. I'm just saying f of x is whatever it may be. I'm multiplying the whole, I'm multiplying the whole function by a 2. So again, as you can see, this is the red curve. The original curve is the red curve, x squared. And the second one, blue curve, is 2 times that. Now, of course, if you want, you can write it that, but there's nothing wrong with it. But you do have to understand, you're not multiplying x by 2. That would have a different effect. You're multiplying x squared by 2. And to emphasize that, let's put a little parenthesis here. Okay, so okay, that has a different meaning. So that won't let me do it, unfortunately, but that's okay. We'll try this one. See if that works. Either it will or it won't. It does work. So I'm multiplying the whole function by 2, x squared. So this is called a vertical stretch. Let's write it down. What does that mean? And why is it called a vertical stretch? And you really want to get it, guys, okay? Okay. Why is it called a vertical stretch? To me, it seems like they're taking the red curve. Here, it's the same. Okay, it's stuck on the x-axis, true. But the red curve is being pushed up, stretched up like this. And by a factor of 2. Well, what's that supposed to mean? Well, not really that difficult. I'll show you right now what this means. Excuse me, I don't know what's going on here, but I'll clean it. Okay, what this is trying to say, guys, if this is 1, this is going to be 2. If this is 3, and when you go up, it's going to be 2 times 6. And it really is. That's why I like Desmos. It's very clear. You can draw on it. So what we are trying to say is if this is whatever this is, okay, this will be 2 times that. And it's called a vertical stretch. What is a vertical stretch? Everything on the x-axis stays where it is. Everything else is stretched away from it. I'll give you one more example. Well, let's pause here a little bit, guys. I will give you one more example, though. Let's pause here a little bit. I don't want to rush too much. And we're going to do horizontal stretch and shrink, and that's going to challenge you guys a little more. Okay, what happens, guys, if I replace this 2 with 3? It'll be a vertical stretch by a factor of 3. It'll be stretched even more. Take a look. Look at what happened. And this relationship, if this is 1, and look, this is 3. This is 3 units. This is 1 unit. Everything is stretched 3 times. So if your height is 1 unit, your height will be 3 units. If your height is 5 units, your height will be 15 units. So what happens if I replace this with 4? You can almost guess. 4 times. I'll show you right now. This line is 1 unit. And this line is 4 units. 4 times stretch. So what is a vertical stretch, guys? Take any curve, multiply the whole function by a number like more. It has to be more than 1. Okay, I'm going to show you in your notes what it looks like. It has to be 1. It could be 1.1. Generally, we're going to see whole numbers. Okay, 2, 3, 4, 5. It's going to be a vertical stretch. Let's pause there a little bit, guys. Okay, just a little bit to see if you have any questions. Okay, guys, I'm going to leave the blue one here, and I'm going to make this a 2. I'll tell you why in a second. I'm going to talk about vertical shrinkage now. It's all going to be vertical. So I'm going to take the whole function. I'm going to call it h of x. I'm going to take the whole function, which is x squared. I can write f of x. Okay, I don't need this for now. Let's hide this. H of x is, this time it's x squared over 2. This time I'm not multiplying by 2, I'm dividing by 2. I'm going to change the color. I'm going to make it green. Wonder what that color was. That was blue. So guys, I don't need the blue curve anymore, but you do want to see what the relationship is between the blue curve and the green curve. The blue curve multiplies the function by 2. The green curve divides the same function by 2. What happens, guys? It just seems like, I'm going to hide this. It just seems like it's called shrinkage. Okay. I'm going to call vertical shrink. Vertical shrinkage. Shrink, it doesn't matter. We'll see whatever your book uses. Vertical shrink, I think that's all they use. But let's just write vertical shrink. Why, guys? Take a look. If the value is 4, red curve, and its corresponding value is half 2. So it's called a vertical shrink by a factor of 2. Okay? When you divide a curve by a solid number, like 2, 3, 4, it's going to be a shrinkage. Now, one thing you do have to understand, guys, dividing something, I'm going to write it here, x squared by 2 is same as multiplying by half. Both are available to us. Sometimes we will say dividing it by 2, sometimes we'll say multiplying it by half. I think your book uses this format, so we have to be familiar with both. Now, I'll pause here a little bit, then I'm going to show you a little trick that you can use when you're looking at these things. So guys, as we have discussed, this time around, especially if you're using Desmos, it's really a good idea to call it f of x. It doesn't matter what your function is. It's going to be f of x. And you multiply the whole thing by 2. Now, you don't need this extra parenthesis anymore now, okay? And here, you're going to take your f of x, and you're going to divide it by 2. You don't need to write x squared. Why is that a good choice? Okay, what do we have here, guys? This blue curve is this one. It is called a vertical stretch. It's going up. The red one is the original one. It's called a vertical stretch by a factor of 2. This green one is called a vertical shrinkage by a factor of 2. Shrinkage means getting closer and closer to the x-axis. Now, the benefit of writing your f of x here is this. Suppose you want to change x squared to x cubed. Everything changes. Look how nice it looks. You don't have to go back and change g of x. You don't have to go back and change h of x. If you change your f of x to x cubed, everything automatically changes. Everything we learned are still valid. One more. Let's do one. Remember today, guys, we looked at the square root function. Let's change f of x to the square root function. And this, if you remember, it's going to look like this. Of course, my curve is not going to be perfect. And of course, you can do to the power half, but I'll write it nicely. Look, now it's very easy to see why what I'm saying makes some sense. Okay, so this is the g of x, the blue one. Let's hide this for now. Is a vertical stretch by a factor of 2. Is it really doing that? Yeah, sure. 1, 2, 1, and this is exactly twice. 1, 2. So it's stretching it this way by a factor of 2. Okay, if you replace this with 3, it's going to be 3 times as high. Okay, well, let's go back to 2. Okay, having said that, let's go back to this. We claimed the green curve is a vertical shrinkage by a factor of 2. By a factor of 2, some people say half, doesn't matter. Take a look. It's going to push it down like this. The red one is the original one. I'm not changing it. By a factor of 2 means if this is 2, this is going to be 1. Sure. Whatever this is going to be half of that. It's pushed down, and we call it vertical shrink. Let's pause here a little bit. Then I'm going to go over the slide in your book, and it'll make a little more sense. Any questions, guys? Don't be shy. So guys, here is the slide. They are saying, let me go back. They are saying that, remember guys, we said our C was, they're saying greater than 1. Our C was 2, 3, 4. Okay. We use 2, 3, 4. That's what we mean by greater than 1. It's called stretching. And shrinking was, our example was half, 1/3, and they're all between 0 and 1. That's really what they're saying. Okay. Between 0 and 1 would be half, 1/3, 1/4, 1/5. All those things will be between 0 and 1. If you multiply the curve by this kind of a factor, remember guys, we said multiplying by half is really same as dividing by 2. That's kind of what we were talking about. I'm going to pause here a little bit to see if you have any question. The next one is a little hard, a little counterintuitive. Okay, guys. The last one. Okay, here's a nice summary. Everything we are going to be wrapping up today will be right here. Okay. And let's see what this one is. So before even we get to this, well, let's take it. It's called horizontal shrinkage and stretch. How does that work? Okay, we're going to go to our Desmos. In the case of horizontal one, guys, and I like the idea of using f of x, and I'm going to take my f of x, make it simple. X squared, I like that. That's a very basic curve. Now this time, I'm not going to multiply the whole function by 2, but I'm going to go inside, replace this x with 2x. And I'm going to go inside, not divide the whole function by 2, but go inside and wherever I see x, I'm going to divide it by 2. Okay, now I'm going to show you one thing. I like this format better. Okay, it makes a lot more sense. What we are really trying to do, if you were to write it, you would say g of x is, instead of x, you're going to write 2x. It's going to look like this. Actually, I'm going to show you one that it really is the same curve. So you're going to go inside the function and replace x with 2x. So let me draw it for you. So the claim that I'm making, guys, I don't need this for now. Okay, I'm going to make another g of x. Okay, another g of x. Well, I guess I can call it g of x. It's going to be the same. And we are claiming I'm going to go inside x. I'm going to write 2x. And take a look, guys. Take a look. This blue function and the green function, they overlap. You don't see any blue. Blue is actually here because they're the same function. If you hide the green, the blue shows up. That's my way of convincing you that this, and this are the same. Okay, I'm going to convince you that h of x, I'm going to write it in the traditional format and convince you they are the same. So let's hide this. I like the f of f format a little better. I'm going to call it h of x. And I'm going to go inside the function. My square is going to be my square inside the function. Instead of x, I'm going to write x over 2. Now, I'm going to show you these two functions. Okay, I don't need the red one. All I'm trying to convince you is that this is same as this. So if I hide the purple, I see the green one. So they're really the same. Now I like this format better. Okay, the F format better. So let's hide them. I don't need them. They're here. If you have a question, we'll be happy to answer. So let's go back to our main transformation stuff. Let's just look at this. What's going on, guys? What's going on? The f of x is the original function, the red function. Okay, to me, it seems like somebody is squishing the red function this way. Now, since you're squishing it from left and right, we call it horizontal. Okay, when you multiply by 2, 3, 4, we're going to show you. It just seems like you take the main function and squeeze it towards the y-axis or the vertical axis. I'm going to show you one more example right here so that you're convinced that look, this will be squished even more. Look what happened to the blue one, went inside. Why? What does this have to do with this 2 or 3? Let's go back to 2. And trust me, guys, this will be, if this is 1, this is going to be 2 throughout. And if you replace it with 3, it'll be 3 times squished. I'll show you right now. What does that mean? Well, that means if this is 1, this is going to be 3. And check anywhere, this is 1, this big one will be 3. So when you multiply inside the function x by 3x, it's called a horizontal shrinkage. Again, you have to see your x function. Original function is the red one, and the new function is the blue one. The blue one is being shrunk. It's shrinking towards the y-axis. If things move closer to the y-axis, we call it a horizontal shrink, horizontal. Okay, the previous one was vertical. Let's pause it a little bit, guys, okay? It's a little challenging, I know that. Any questions from anyone? Okay, give me 1 second. I'm not gonna talk, but I'm gonna turn down the volume of my phone, okay? Sorry about that, guys. Any questions, guys? Okay, so guys, we have 10 minutes. I'm going to show you the next one. It won't take me 10 minutes. Okay, so I'm going to hide the blue one. I don't need the blue one. Blue curve. What happens, guys, if I go inside my function, look at the red function, and I divide, replace x with x over 2. What happened? This is something horizontal too. Why horizontal? Your y-axis stays where it is. It just seems like the red one is the original one. It just seems like the red curve is being pushed out. So it's called a horizontal stretch. Again, by a factor of 2. How do I know it's 2? Look, if this is 1, this whole big thing is 2, twice as large. It's stretched out twice as much. So if your height was 6 feet, original height, this is going to be 12 feet now. And real quick, if you replace it with 3, what happens? It'll be stretched out by a factor of 3. See, the green one is even farther out. And if you try to measure it, it'll be exactly 3. This is 1 unit. I'm going to use a different color. Right from here to here, it'll be 3 units. I know you can now see you cannot see the green, but if you measure the pink line, it'll be 3 times the green line. So when you divide, go inside the function, take every x and replace it by x over 3, it's going to be a horizontal stretch by a factor of 3. It's a little counterintuitive. You're dividing it, it's going to stretch, but the answer is yes. And when you go inside the function and multiply it by a factor of 3, it's going to be a horizontal shrinkage. Yes, it's a little counterintuitive. You're multiplying, but you're getting a shrink or shrinkage. So let's look at this one. Take a look. The red one is the original one. This one, it's pushed this much. what does this have to do with the factor of 3? Well, it's exactly 3 times. If this is 1 unit, all of this is going to be 3 units. You can test it anywhere. 1 unit, there's going to be 3 units anywhere. So, any questions on horizontal shrinkage, horizontal stretch, vertical shrink, vertical stretch? A little bit of recap, guys. When you're doing vertical, you multiply the whole function by 2. It's going to be a vertical stretch. If you divide the whole function by 2, it's going to be a vertical shrinkage. When you're doing horizontal, you go inside the function, replace x with 2. It's going to be a compression or shrinkage. Some people use the word compression. I don't think your book does. And when you go inside the function divided by 3, it's going to be a horizontal stretch. So here's the deal, guys. I have all my slides here. Okay. It's gonna kick me out in 6 minutes. And the plan is to come back. I'm not going anywhere. The plan is to come back and do some of the problems from our text. I think we're done with the notes. So let's wrap this up and see you guys really soon. Okay.